Our speakers are all going to speak for about 15 minutes each. And at the very end, just after 1 o'clock, we're going to have a Q&A with all of the 4 panelists together. So please, I urge you to put your questions in the Q&A box, which is just along the bottom of your Zoom panel. If you pop it in there, it means that I can see it and I'll be the one asking the questions directly to the speakers at the very end. If you're having any big issues, you can't hear, you're struggling, everything's really difficult, please direct message Lou, who you can see here, Louise Butt, or Victoria May Chamberlain. They'll be able to help you with any technical problems, because I'll be the host, I might not see them. So don't message me directly if you can avoid it. And without further ado, I think that's all from me. I want to get started. I'll leave it to kind of Dr. James Darling to kind of kick things off. James is a reader in Earth and Planetary Materials at the University of Portsmouth. And I think he's going to talk to us a little bit today about moon rock and more, I'm sure. So I'll hand it over to you, James.
Oh, great. Thank you very much. So I'll just share my screen. Hopefully you can all see that now. Good. So, well, thank you very much. It's, I'm really excited to be here and just to talk a little bit about the work that we do with lunar samples and why that's important for understanding of planetary geology. So without further ado, let's just start with a broad scale perspective. I mean, the moon is not only wonderful for many reasons that we just mentioned, it's a unique record of the early evolution of the Earth-Moon system. On the Earth, we have a relatively young surface to our planet that is, reworked by pesky processes like plate tectonics and weathering. Whereas on the moon, you have a very ancient surface, which can tell us about roughly the first billion years of solar system history. So what we like to do is combine observations at many different scales, from global data from orbital spacecraft, satellites, through to this wonderful image of Apollo 17 astronaut sampling on the moon. This is Harrison Schmitt, who was a geologist on the moon's surface, and have that appreciation of the stories that rocks and soils and minerals can tell, while sampling for science was really powerful in terms of our ability to answer big questions in lunar evolution. And then a lot of my own research in my research group in Portsmouth, we study these materials at the microscopic scale, all the way down to the chemistry of tiny volumes of material. And if you link all those things together, you can really address some really big questions in planetary evolution. So let's think about some of those big questions that we like to address. Here we've got a lovely rotating view of the moon from the Lunar Reconnaissance orbiting camera, which is a spacecraft that's been orbiting for many years now. And we can, with that data, look at the far side and also look at topography of the moon. So this is a colored topographic map, if you like, where blue is very low topography, yellows and reds are very high. And the topographic map really picks out some of the key kind of features that we see on the moon, specifically the lunar highlands, which are covered in these impact craters, and then these flat mare, which are volcanic terrains, which are a little bit younger. And if we settle on the far side here, a view that we don't get very often, we can see some of my favorite geological features in the solar system. We've got the Orientale impact basin down here on the lower right. This eye-like structure, which is about 800 kilometers in diameter. And that's way, way, way bigger, about 5 to 6 times bigger than the impact structure that led to the extinction of the dinosaurs, for example. So these are huge events with massive amounts of energy. And even Orientale there is dwarfed by the South Pole Aitken Basin, which is well over 1,000 kilometers in diameter and forms the South Pole structure of the moon. So there are, this wonderful record of early solar system processes available to us. And in terms of the big science questions that we want to investigate, I've just copied and pasted these from the upcoming NASA Artemis program mission summary. These are 3 of the big headline science issues for the Artemis program, which will hopefully put crewed missions back to the moon by 2024. So very exciting. And so these 3 big things that we want to try and better understand about the moon. Firstly, its record as a time capsule of that early solar system evolution and how planets form and evolve through that first billion years or so of solar system history. We want to understand volatiles, because volatiles means water for one. It also means things like hydrogen and oxygen, which might be used for fuel from the lunar surface. So we can understand, volatiles in the solar system, how they came to be on planets, where they're distributed in the crust, and how can we access them. And we also want to understand the impact history, largely because these individual giant impact basins are global killer events, right? So they happened a very long time ago, but from the perspective of astrobiology and understanding the evolution of life, we really need to understand when they happened and what effect they had on the crust and structure of not only the moon, but as our nearest neighbor, also the Earth as well. Because if these massive impacts were affecting the moon, they certainly would have been affecting the Earth as well. So some really big science questions that remain to be answered in the future, but they're things that we can start to tackle through looking at lunar materials that we have available to us. So with that in mind, in this hand, I know you won't be able to see it very clearly, but in this hand, I have an Apollo 15 sample, which was returned from the lunar surface in the 1970s. And in the other hand, I have a lunar meteorite. So lunar meteorites are, give us a broader sampling of the lunar surface. They're fortuitously for us, knocked off of the lunar surface, captured by the Earth's gravitational field, and then land somewhere, in this case in Northwest Africa, and we're able to collect them and study them to understand more about lunar evolution. So I want to just take you through a brief tour of different scales of which we kind of study lunar geology and study these samples. So let's start with broader scale in terms of our understanding of, particularly for the Apollo samples, where they came from on the lunar surface, the geology in the area. But for example, with Apollo 15, the mission targeted the edges of one of these very large impact basins, where you have the boundary between what looks like highland material, the light material that you see from Earth, and the mare volcanic plains, the dark material we see from Earth. And so at least we have some context as to where these materials came from. We can delve a little bit further. NASA were fantastic at capturing the audio and video and image logs for the mission, so we can reconstruct where our samples came from on the lunar surface. This is Apollo Station 7, which is where this particular sample came from. And in fact, this is the rock on the moon's surface. So, I'm holding a rock in my hand, or a piece of it, and that's where it was sampled in situ on the lunar surface, which is really, really, amazing. And I feel very privileged to be able to work on these materials. But that context is important scientifically as well. That's what we do with undergraduate geology students, for example. We take them out in the field so that they can read the natural world around them, figure out how best to answer big problems in natural sciences by understanding context for materials. So these images give us fantastic context. And then here is the rock. Okay, bear with me, because I completely appreciate that on first glance, you'd probably think this is a boring brown rock. And if I showed this to you without any context as to what it was, it would just be a boring brown rock, right? It's a bit cruddy looking, it's a bit gray, brown, some whitish bits. Bleh. We've all seen rocks like this lying around and gone bleh. But the beauty of this specimen is in the information that it contains, right? So this is collected on the lunar surface. It's, if you like, a time capsule for inner solar system evolution, not only lunar geology, but what happened to planets in our inner solar system. So, the beauty of this specimen is in the detail in terms of its structure, its composition, the geochemical data that we can extract from it. And so, this is a really, really special sample and one of many collected from Apollo. But I did want to emphasize that there is beauty in geology, right? So this is a gorgeous picture of the same sample. It's actually the slide that I have in my hand, where we've mounted the sample on a glass slide and polished it so it's very thin. And that means that we can do optical microscopy because it becomes transparent to light. So this is an example of an optical image. The field of view is around 0.5 millimeter in diameter. And so we can use the colors and the textures that we see in this image to tell us about which minerals the rock's made of, how they welded together, and that tells us about how the rock may have formed and been affected by external processes like heating and deformation. And in this case, it has quite a complex structure because it was essentially a series of rocks welded together during a meteorite impact event. So we can say a lot through microscopy of samples such as this. But we can delve deeper still, and we can use specialist microscopy techniques. And this is something that we do a lot of at the University of Portsmouth. We do electron microscopy. And here, so the field of view in this particular image is 15 microns across, which might not mean too much to you, but it's essentially about 1/10 of the diameter of a human hair, roughly, on average. So we're now looking at things in very great detail on the small scale. And the important thing that I just want to highlight here is it allows us to better understand processes that have affected the rock, but also target specific minerals. So the bright phase in the center of this image is a uranium-bearing mineral called bdelliite. And uranium decays to lead with a very well understood half-life, so we can use that mineral and its chemistry as a clock, essentially. It gives us a radiometric clock with which we can date when the rock formed, and also, with some careful analysis, how it and when it was affected by secondary processes like impacts. So electron microscopy, something we do a lot of, and I lead electron microscopy facilities at the University of Portsmouth. And we apply it to a wide range of things, from planetary samples to biological material to engineering samples. But ultimately, this same kind of technique can tell us a lot about materials in great detail. One example of that, if my slides work, there we go. One example of that is this map. This might not look like much of a map, but this is a map of the structure of one of those teeny tiny bdelliite minerals. So the map here is telling us the crystallographic orientation of different parts of one of those tiny grains. And so we can map things down to nanometers in scale, so billionths of a meter in scale, and really understand its structure. And that's important because the structure is affected by those secondary processes like impacts, heating, deformation, volcanism. And so we can build up a history of the material from microscopy techniques such as this. And this is a technique called electron backscatter diffraction. Essentially, we're firing electrons at the sample, they're diffracting through the crystal lattice, and then we're building up a map of the orientation of the crystal structure. But we can go further still. We can always go smaller. This is now a data set showing, the spinny data set in front of us is showing us the position of individual atoms in one of these samples. So these are iron atoms in another one of these bdelliites. So the total field of view is just a tiny fraction of a micron, a few hundreds of nanometers in scale. And the reason that we might want to image individual atoms and their position is to link the chemical knowledge that we can gain from these minerals with that structural evolution that we can get from things like the electron diffraction techniques. And if we can pull those two things together, we can really tease apart in great detail how these rocks have formed and been affected by different processes. So techniques such as atom probe tomography here not only give us cool spinny atom plots, but can tell us a lot about how materials have responded to deformation. And ultimately, we can piece that all together to build a history for a particular sample, which might, in this case, the y-axis here is the age in billions of years, or giga-annum, GA. And we can tease apart different processes that have affected a particular sample, and therefore build a better understanding of the lunar crust. And I'm just going to step back out again to say, well, if we apply these techniques to the right materials, we can say new things about samples that were collected in the 1970s in the Apollo program, and we can build a better understanding of how the lunar crust had been affected by impacts, how it formed, where the volatile elements are concentrated, and so on. So we can say an awful lot about lunar history from microscopic techniques. And I just want to finish with a few pretty pictures, basically, just to show the beauty of geology when you use a microscope. This is the same sample that's in my hand. Again, just wonderful colors, textures, fabrics, all of which are important for its history. Another material, another Apollo sample that we've been working on quite extensively. In this case, we've recently shown that this rock was formed in a giant meteorite impact melt sheet 4.3 billion years ago on the lunar surface. And that was a new conclusion from a material that's been studied for 40 years or so. This wonderful image is of lunar regolith collected in the Apollo missions. So when we come on to think about resource exploitation on the moon, living on the moon and using material around us, this is the kind of material that will be, that dusty regolith that astronauts will be dealing with. So we can use microscopy to better understand it. I threw this one in because it's pretty and it's a rock we've been working on a lot, but it's essentially a meteorite that's one of a series of regolith that's been welded together in an impact event. And then in detail, this is a much more high resolution electron microscope image where you can see so many different textures and fabrics. There are swirly things, which are where the rock has melted. There are bendy things where it's been deformed, fractures, fragments, all these wonderful textures and things to be seen on the microscopic scale. So finally, I'll just say, this is a really exciting time for planetary geology. And I think integrating those global scale data sets, like I showed the LROC data, with the microscopic information we can now get from these samples, pull those two things together, and we can say a lot about planetary evolution. And looking ahead to the Artemis program, where we'll have men and women on the lunar surface, hopefully in 2024, we're going to have great opportunities to better address some of these big science questions. Okay. Thank you very much.
Thank you so much for that, James. That was absolutely incredible. I, for one, did not realize how beautiful the samples could actually be. So that was really fantastic to see. And it's really great to see how much detail you can get from what is essentially a tiny sample of rock. It's amazing. So thank you very much. I'm sure you've got loads of questions for James. I can see some popping in the Q&A now. If you do have more, keep putting them in there because we will be able to answer them at the very end with all the panelists together. So thank you very much for that. And now I'd like to introduce our second speaker. So this is Professor Mariana Abris. So she currently is the Professor of Multisensory Interfaces at UCL. And before that, she was working as head of the Sussex Computer Human Interaction, or the Sky Lab, at the School of Engineering and Informatics at the University of Sussex. That was a big mouthful for me, but I'm sure she's got a lot more to say about her work and how, how that relates to the moon. So without further ado, Mariana, I'll hand it over to you.
Thanks very much, Chloe. And first of all, thanks so much for inviting me to this exciting series of talks. And as in so many other places, I usually feel like an intruder, like an alien, because my research is not really around the moon or space specifically, but it's a passion I pursue all along. And I'm really excited to be here and listen and learn about the moon. What I'm going to do is the next 15 minutes, I'm trying to take you on a little journey and give you a little flavor of my view on space, moon, Mars, or whatever kind of explorations there are still ahead of us in the future to come. And I gave it the general title, Experiences in Space, because one of the key things I'm doing as part of my research is really taking a human-centered approach on how we design experiences, how do we develop new interactive systems. And I'm doing that as part of the Department of Computer Science at UCL, and there particularly as part of the multisensory devices group. The 3 areas of touch, taste, smell is just a sub area what I focus on, and which is really, as Chloe said, emerged from the lab I started at Sussex University, the Sky Lab, around multisensory experiences, and mainly funded by the European ERC. But the multisensory devices really tries to bridge the complete continuum from basic science, engineering, interaction techniques to human factors. And the human factors, and now the sun is coming in as well, are really where I'm focusing on. And I just wanted to give you the kind of driving question of the research I'm doing around multisensory experiences. And that's really, what kind of multisensory experiences can we design for, and how do we do that? Especially if you think about your sense of taste and smell. I mean, do you want to use tubes in your mouth? Do you want to clip something around your tongue? Do you put something in your nose? That are not quite nice experiences, but sometimes they are the experiences and used in experiments. But we are trying to really imagine new ways of creating olfactory, gustatory, and tactile experiences, which ultimately bring all the different senses together in the way we interact with technology. So what does that have all to do with space and the moon? And I think when Chloe contacted me, I asked this question myself, because why would you contact me? And I think that is where I always like to start think about what makes us human. And that's, how do we engage with the world around us? And that's through all our senses, especially when we are young, when we are children. We put our nose everywhere, we touch everything, we put things in our mouth. Basically, the world is like an amazing mystery and space to explore and to experience. And then we look at space, and that's when we are kind of hidden away inside a suit. We are kind of having this border to protect us, obviously, but that doesn't allow us anymore to engage with our surrounding, explore our surrounding, and really kind of make those multisensory experiences we would usually have. And even if you're not inside a spacesuit, inside the ISS, inside spaceships, we often not really surrounded with the environment we know from Earth. You don't really have much of those kind of diverse textile or tactile experiences. The tastes and the smells, they might be not the ones you look for, but there are certainly certain smells in there. But what does that do to us, to our well-being, to us as humans, to not just kind of like perform well, but also to feel well, especially when we think of long-term missions into space. So how can we create future space travel in such a way that we preserve the humanness, that we really kind of like make use of all the human capabilities we are having? And there is actually quite an increased effort within my research community, which is human-computer interaction, to see how we, coming from a user-centered design perspective, can make a difference and our own contribution to future space explorations, settlements, explorations, and so on. So this was something where we had a workshop last year as part of our main conference, and we had over 100 participants. Well, that was maybe also facilitated to the fact that it was done online and remote, as so many conferences over the last 18 months, which, however, still showed that there's a lot of interest in that particular area, and there is appetite for creating new interfaces, new interaction concepts in order to really support all the efforts from the different disciplines, which are really at the core of enabling people to go into space and do all the fascinating research. And what I would like to highlight is one of the research I have done around eating in space, or designing food experiences in space travel. And I always go back to this opening lines in the book Endurance from Scott Kelly, A Year in Space, A Lifetime of Discovery. And I don't know if you remember, the opening of the book is when he's talking or sitting at the dining table with his family, just being back from space. And everything is kind of like, for everyone, seems so normal, but for him to just have a fork, to lift a fork, and to have this social surrounding and experience in eating is something which suddenly became so important, having been deprived of this routine and these opportunities over the past year in space. And I think that is one of the things we also wanted to explore further. So that was a collaboration with colleagues from the Norwegian Business School, Carlos Velasco, but also from Lining Yao at MIT Media Lab, and a food designer from San Francisco, where we try to understand how can we conceptualize eating experiences in space for non-astronauts. And that means for the everyday person, it might not be the everyday person who is going to be able to go in space very soon because of all the costs and so on. But we wanted to really pick up on the developments we have seen. It's not just astronauts going in space. We see a lot of private space agencies which are now putting people into space for short periods. But looking far in the future, everyone might go on a holiday in space. Allow me this kind of provocative statement, but who doesn't want to at least feel like an astronaut at some point, or eat like an astronaut? When we see Tim Peake floating around, it's just one of those awe-striking elements which are really exciting. And so we did this particular piece of research where we try to conceptualize eating experiences in space. And we thought about, like, you have Earth, you have the ISS, and then you have the Moon, the Mars, Saturn. So there are different time frames, and different time frames also put different kind of aspects into the center of attention of how we design eating experiences. Because if it's a short period of time, you might be happy to just get over it and eat whatever is provided. But if we are talking about weeks and months of being out there in this particular confined space, what are the kind of like requirements, needs, desires of people? And so what we did is we did a crowdsourcing study, an online survey with over 200 participants based in the UK, where we applied qualitative and quantitative measures in order to understand their preferences, but also their desires and expectations of what would it be like to go on a short trip or on a longer trip, either to Moon or to Mars. And so we analyzed the responses of participants from the survey, and we tried to cluster them. And so there were 5 main areas which we identified as very important. So the functional elements, so it contains nutrition, health, balanced diet, vitamins, and so on aspects. So something which is done very well by the space agencies as well to ensure the health and safety of their astronauts since the last decades. But there is also the sensorial aspects, like which really refers to the food texture, to the smells, to the tastes and flavors, the freshness, the crunchiness. So all the sensorial experiences, which we take often very much for granted. And then there are the emotional aspects, social and environmental. So the emotional is really about this reminder of home, or the favorites we have, these treats, which we might start missing if we are going on a longer space journey. And the social aspect, well, you might not be able to take your whole family with you if you're going on such a trip. It's maybe most likely just you and your family partners, your community stays behind. But how can we actually think about these social aspects as well? How do we ensure that you are staying connected to the loved ones? Because they are so essential when we are eating. Again, we take it for granted that we sit down on the dining table and then share a meal, or if it's just something fast, we take something, grab something and talk and walk and eat. But how do you do that in space? And also the environmental. We often forget that food is not just like what you put in your mouth, it's also the context where you are eating. It's like the atmosphere, it could be the lighting, the temperature, all the different things. So even the subtle things like the dining table texture, the cutlery, the napkin, all that contributes to our eating experiences. So how can we take all this into account? And I mean, I only have a few more minutes left to conclude that, but we have written that up in a journal article in Frontiers of Computer Science, where we present 3 concepts about potential eating experiences in the future, which are around spice bomb mixing, flavor journey, 3D printing, and eat memory bites. They might not, these are just the titles, so they might not tell much, but I just show you a glimpse of them. So one of the things we know when you're going into space, your olfactory and gustatory sense are going, so your smell and taste perception is going to be affected. So your nose might be blocked, and the nose or the sense of smell contributes highly to our taste and flavor experience. So if you can't smell, you might enjoy less your food. So a lot of kind of condiments are contributed into the packages for astronauts so that you can spice it up. And what we were thinking is as a first concept, so you can allow people to mix different ingredients and you put them into this pot, if you wish. It's just a design concept. So you can start mixing different flavors in order to increase that. And then it's not just about mixing it and kind of giving it more spice to the food which you're eating, but you're also making this kind of spice bomb or this kind of container a playful social element. So you can share it, so you can close it and you can share it between the different passengers and shake it around. And the more you shake it, the more spicier it gets. And so you have the social playful element alongside to enhance the flavor experiences. So that is one. Another concept is we are missing this kind of like flavors from home, or we would like to kind of have some variety where you have softness and crunchiness and different textures involved. And how do you make sure that it's not always the same weekly menu? How can you bring in some variety? And how can you link that back to your family, friends, or chefs back on Earth? So we imagined this kind of like workflow of a flavor journey for the printer, where you can set an order of food you're craving or you would like the ingredients, and then a flavor profile is created and the recipe is made with influence of maybe a chef or a family member. And then you have a food 3D printer in space, which helps you then print it. And again, this is something where you have done a certain form of printing, and then it has the different textures and flavors, maybe even temperatures of heat and coldness included as well. And with all the advances in 3D printing, I think there are lots of opportunities here as well. But as I was saying, it's also the context. It's not just about what you eat, but also where you eat. And so the last one of the concepts is Earth memory bites, where you capture a certain scenario. Let's say Brighton Beach, where I'm living. I want the Brighton Beach captured, and this is kind of simulated in space. Let's say a virtual reality environment or a projection mapping. And so I can create this environment where I then eat these memory bites and can share them with other passengers. So I can also share my culture, my background with other people and can enjoy that in space. And so basically what I would like to encourage is to just think about how can we bring more of the sensory experiences into space when we are designing those space travels in order to really ensure the health and also the well-being, emotional well-being of people traveling to space. And I wanted to conclude with this quote from the world is but a canvas to our imagination, which is something which keeps me inspired in the research I'm doing. Thanks very much.
Mariana, that was amazing. I, for one, have never thought so much about all the different elements of sensory experience when eating. And it's really exciting to think about how you can kind of transport that, not just for astronauts, but for normal space tourists in the future. So yeah, thank you so much. That's really great. I really thank you so much. So everybody, please, if you've got questions for Mariana, please pop them in that Q&A box. I know we've had a few coming in already, but please don't be shy. Anything, there's nothing too daft to ask. And I know that someone's got their hand up. If you just pop a question in the Q&A box or send an email, a little e-note to Victoria or Lou, they'll be able to help you. So now we're on to our third speaker, who's taking us on a totally different celestial journey, which is great. This is Rod Mamin. He is the COO of a company called SpaceBit. His background is, I think he's a Master of Maths and Computer Science, and his background's in IT, but now, since 2014, he's been focusing all his entire activities on space. And SpaceBit are a really exciting company who are looking at sending robots to the moon very soon. I'm sure Rod will love to share more. Over to you, Rod. Rod, for some reason, we're not able to hear you. So I'm not sure if it's a little setting there. It might be something to do with the little headphones. I'm not sure.
Can you hear me now?
Perfect. That's great.
Okay, something happened with my headphones. So I want to say thank you so much for the invitation. And today I'd like to briefly tell what's going on with the commercial lunar space exploration and briefly describe what we are planning to send to the moon next year. So I'm working at SpaceBit. We are a UK-based company. It was founded in 2014 by Pavlo Tanasiuk, and our goal is to explore lunar surface with smaller robots. First of all, I'd like to start with the explanation why we decided to focus on the moon. We are a group of people who really believe in space exploration, and we really believe that humanity must go to other planets as soon as possible. And from our perspective, the moon is the best candidate for the first extraterrestrial base. The reason is, well, the main reason is quite obvious, because the moon is quite close to Earth. It takes around 3 days for the astronauts to go there. Or if you send a robotic mission, it could take up to 30 days to get to the moon. But in any case, it's quite fast. Another huge benefit of the moon is that it has no atmosphere, and it's quite easy to launch ships to other planets from the moon. Of course, it'll take a lot of effort to send all the supplies to the moon, but we believe that with time, a lot of supplies could be produced on surface of the moon directly. And from our perspective, the last reason to why moon is so important is that now we know for sure that there is water on the lunar surface. And water means that well, humans can live there for a long time, and it means that one type of rocket fuel could be produced there: oxygen and liquid nitrogen. Oh, sorry, hydrogen. Despite that, there is a nice thing on surface of the moon that is called the lava tubes. Basically, there are quite a lot of photos from lunar orbit with a really interesting holes in lunar surface. And often these holes are connected to tunnels, and on the right image you can see one tunnel. It looks like, you know, just some kind of a cord on surface of lunar surface. Most probably these things contains a lot of internal volume that could be used to build a human base. Lunar lava tubes were discovered not so long time ago, I believe maybe in 10 or 15 years. Right now, I do not remember the exact date. And after that, a lot of proofs were found that these tubes could exist. Basically, lunar lava tubes is almost the same as Earth lava tube, and lava tube is just a very specific type of cave. If you're interested in what it's exactly, it's not an issue to find a lot of useful information in Google. I'd like to show you how lava tubes on Earth looks like. And in the top left corner, you can see a photo of the lava tube in Hawaii. I've taken this photo from Wikipedia. And basically, it's just, lava tube is just a long, long tube. And these tubes, on lunar surface, these tubes can provide us with a quite stable temperature. According to several researchers, average temperature in lunar lava tubes would be around -20 C. It's quite warm, I have to say. They also provide protection from radiation, from meteorites, and well, it would be really handy to build a base in such a tube. Several years ago, we went to Japan to meet Dr. Haruyama, who is one of the first people, one of the first researchers who published one of the first papers regarding lunar lava tubes, and we made some measurements and tests of our robot inside the lava tube. Here is a photo of our experience. Another important thing that I want to share with you today is that in the next few days, several commercial companies would fly to the moon. And from my perspective, it's really unbelievable. At this point in time, I know about, I think, 4 or 5 already confirmed missions to lunar surface. We are flying with the Astrobotic first mission on the Peregrine lander, and most probably we will have some space on other landers. On the image, you can see several companies who are working on, and their landers who are working commercially on lunar space exploration. Unfortunately, all of these companies except iSpace are from the US. So today, the US is the most, well, they lead in the field of lunar exploration. Despite the Artemis program, there is another really interesting program in the US called CLPS, or Commercial Lunar Space Exploration, or something like that. And the thing is that several years ago, NASA changed their strategy. Previously, they act as an engineering company, so they design everything internally. And several years ago, they decided to change their strategy, and now they act as a customer. So they want to explore the moon, and instead of building their own landers, they ask several commercial companies to do those landers for them. And this program really put the limits, and now in the US, I think 4 companies. I forgot to mention Firefly Aerospace. So 1, 2, 3, 4. So in the US, at least 5 companies, 5 commercial companies aiming to reach the moon in the next few years. And right now, unfortunately, I know only one company, not from the US, and it's iSpace, a company from Japan. They, as far as I remember, they plan to send their lander next year or maybe in 2023. In any case, today, if you want to send something to the moon, you just have to pay around $1 million US for 1 kilo, and in the next few years, you'll be able to send something to the moon. At Spacebit, we decided to use this possibility, and we are sending the first LEGT rover to the moon with the first mission with Astrobotic next year. Here you can see an artistic render of our robot. It has a body, and body size is around 10 by 10 by 10 centimeters, or basically 1 U, and it has legs. We really believe that small robots would be able to explore lunar surface much faster than ordinary huge wheeled rovers. So we decided to go with legs because legs can traverse rough terrain much easier. This robot is quite small. It weighs around 1.5 kilo. It has 4 watts solar panels. It uses Wi-Fi link to communicate with the lander. So basically all the communications from our robot to Earth would be held through a lander, through Astrobotic Peregrine lander. The length of legs is 22 centimeters. And it has several sensors. It has radiation and temperature sensor on board, and it has a simple LiDAR sensor, 1-point LiDAR sensor. Also, it has cameras, so we are planning to take several photos of the moon, take some measurements, and in general test if it's possible to run walked rover on the lunar surface. The first mission should happen next year, and we also, during that mission, we will take measurements of lunar, well, actually of temperature inside our robot. The goal of the first mission is to go for 10 meters. I know 10 meters may sound like quite a small distance, but you have to understand that it's moon, and even 10 meters would be a huge success for us, because it's really hard. In general, we believe that in several years, maybe in a decade, there would be a lot of robots on the moon that would explore lunar surface in an automated manner. So our goal is to send a lot of small robots and create a network, a mesh network of robots on the lunar surface. The reason why we decided to go with small robots is that in space, mass means money, and to send one huge robot, it takes you a lot of money. And in case one huge robot fails, it means that the whole mission failed. And in our case, we believe that we can send several small robots. And if one robot fails, it won't be an issue because other robots would be able to achieve the mission goal. Talking about the moon, we have to talk about lunar day and night cycle. Here on Earth, one day takes 24 hours, and one lunar day takes about 40 days. It means 7 days of shadow and 7 days of light. Lunar day takes 28 days, and it means that 14 days of shadow and 14 days of light. During the lunar day, temperature on lunar surface can reach up to 120 degrees C, and during the lunar night, temperatures can drop up to minus 170 C. Almost all the missions that would be sent in the next few years, I'm talking about commercial missions, won't be able to survive lunar night, because to survive lunar night, you need a really strong source of heat energy. And frankly speaking, today the easiest way to survive lunar night is to send I forgot the name of the device, but basically it uses radiation to heat the rover. So later we'd like to create a better rover that is called Mother Rover. It'll be able to hold up to 4 Asagumas, and it has a quite strong thermal protection, and it'll be able to survive lunar night. The ultimate goal of our missions is to explore lunar lava tubes, and the way we'd like to explore lava tubes is to send a swarm of robots inside these tubes. They will form some kind of a chain, and data will be passed through this chain to Mother Rover, and then through Mother Rover to Earth. I believe that's all I wanted to say today. I'll be happy to respond on any question.
Rod, thank you so much for that. That was really exciting to see what you guys are going to be doing really soon, sending these little robots to the moon. And yeah, I'm really intrigued to see how it goes. So all our fingers are crossed for your first 10 meters, fingers crossed. So what, thank you. Yeah, thank you so much. And like I've said to before, please do, if you've got any questions for Rod, even if they're specific, whatever they might be, pop them in the Q&A box, because he'll be able to answer them after our next speaker. So thank you very much. And now our next speaker is Dr. Nelly Benney. Nelly is a designer of experiences. She's a creative director. She is, well, I don't know, she's got so many job titles, I don't even know where to begin. The design of experiences at the SETI Institute, which is the Search for Extraterrestrial Intelligence Institute. And she has been working in the space sector for a really long time now, a whole over 10 years, I would say. So I would love to pass it on to Nelly.
Thank you so much, Chloe. Thank you for putting this amazing event together. Thank you to my colleagues as well for this incredible presentation. It's been a brilliant morning. Actually, who needs to eat when you have the best intellectual food being presented and shared with you? So look, thank you so much for the introduction. I'm just going to go straight in there and actually stop the noisy people that are messaging me on WhatsApp at the same time. Here you go. So off you go, everyone. Bonjour, bonjour, you all. Alors, so a bit of a warning to you all. This is going to be filter fantastic heavy, this presentation, as for most of us, you know, I mean, until Facebook and Instagram went down yesterday, I was very heavily involved with Instagram filters, and actually maybe some of the people that are watching us are actually maybe students from Portsmouth University, and I'm sure they're familiar with these kind of things that are, you know, sharing popular understanding of the moon in a way. But anyway, so we're going to speak about radical imagination together. And it's a bit, you know, and I'm going to speak about a few projects as we go along. And as I mentioned, and as Chloe mentioned, I'm Nelly Benney Yoon, and I speak with a very strong French accent. Chloe mentioned that I've been in the space industry for quite a while, but not only that, I've been in the UK for quite a while, but for some reason, this accent is still up and running and pretty epic. You mentioned it, I have multiple different job titles, but that will make sense because, you know, I realized quite early on, especially straight after I graduated, that if I wanted to make really big scale projects, I needed to actually have not one job, but have about 15 of them. So 15 different email addresses, so that if someone was to tell me, no, you can do this project, no, Nelly, we don't want you in our institution, then I could go after them with another email address. So, you know, if you tell me no on my WeTransfer email address, then you might tell me yes on my Wired email address, or you might tell me yes on my UN email address, and so forth. So I call this the total bombardment. And actually, Chloe mentioned it, but I run a studio in, well, on a train carriage, actually. It's literally in a train. I mean, you can see here, I'm in a train. Here you can see Juliette working. I have Ayana right there with our fabulous assistant director. We're working on a big festival at the moment, so she's busy typing. As you can see, it's literally a tube carriage, and we are on top of a nightclub in London. Weird place. We can talk about this a bit later on, but today we are all about the moon. So bear with us as we go through it. So just a quick introduction as to what we do in this train carriage. we design experiences. So we put together experience for members of the public to experience a bit of the sublime that is into science, right? So things like making dark energy in your kitchen sink, you know, if you were to be able to produce a bit of the unknown that is allowing the universe to be in permanent expansion. What if you could reproduce an experiment dated from 1927, the Casimir experiment, for example, while you have a microwave gun in your kitchen sink? What if you were able to actually experience a bit of the thrill of our world with a volcano inside your living room? What if you were to experience, you know, a Soyuz rocket, which is a Russian rocket, you know, which actually is not being used anymore, but to go to the moon and do this. And so in this kind of experience, of course, it will be completely meaningless, or it will make absolutely no sense if we were to develop it in a silo, right? And I think we're going to probably talk about it during the panel discussion, but collaboration is key to the way we function in the studio. So we will work very closely with scientists in order to give you an experience which is as close as it can be to the real thing, right? So when I say to you, you're going to experience a sonic boom inside a tunnel, then you're going to experience a sonic boom because we actually work with the scientists that are in the Super Cameo Kende in Japan that work in an experiment that look like this. And they provided us with a soundtrack, and then we work with the soundtrack and we kind of develop this all experience so member of the public gets through it. We also do very weird kind of like extreme experience. We train people towards disaster management, like, you know, firefighter. This is at FEMA in the US. We take students in places like Chernobyl, Reactor 4, in all of the most extreme places. We hunt the worms of hell in deep cave in the middle of South Africa. And we put together orchestra at NASA, for example, to actually give you or give scientists also an opportunity to think through the future of space exploration through music. And everything we do is really triggered towards critical thinking and making sure that whatever is being done in the space industry is actually done thinking in terms of history, acknowledging humanities, and kind of bringing this. We also run a university that, you know, is basically free and accessible to anyone, and kind of teach students how to basically work within the institution to modify them from within. Because let's be real here, while we are talking about space, we have a true problem, right? As a community, as a space community, and I work at the SETI Institute, which is a search for extraterrestrial intelligence institute, and the Astronautical Federation, we work in environments that look like this. This is the place where I spend most of my time, in fact, and this is where the future of space exploration is being decided and discussed. This is where, you know, there is real, true decision being taken. That's a meeting at the Astronautical Federation, to give you an idea. And this is a place where you only see one type of people. You know, sorry for anyone here that is, you know, but, you know, we're talking heterosexual white male discussing about the future of space exploration and discussing about what the future on the moon should look like. Now, I don't believe that this is a good and fair representation of what humanity is like. And of course, this is very much reflected in the kind of the current vision that is available to us, which are extractive visions of the moon. And in a nutshell, a complete repeat of history. So what I want to talk about today, well, of course, I'm already, you know, well over time, but anyway, what I want to talk to you about today, and I'm just going to jump straight in there, and then maybe we have time to discuss about current project we're working on, but I want to discuss this notion of radical imagination, right? I believe that while we are going to have a conversation together, we should really start to consider this notion. You know, the fact that, and for those of you that are not familiar with these terms, I'm just going to kind of like have a quick conversation about it. So radical imagination is the ability to imagine the world, life, and social institutions not as they are, but as they might otherwise be. It is a courage and the intelligence to recognize that the world can and should be changed. The radical imagination is not just about dreaming of different future, it's about bringing this possibility back from the future to work on the present to inspire action and new form of solidarity today. So this is a part of a book called, well, Radical Imagination. And it's really the idea of like actually starting to define and design platform for collective experience to be taking place, but also places where we actually acknowledge the past and actually work with the past in the present. So what I would love to speak about with all of us today is when we think about the moon, how about we start to reflect about the moon and we think about it in the context of radical imagination? What if we weren't to actually just repeat the eel of the past and just again going into going into the moon like we went and like Europe went and colonized the entire world, like say, and actually start to figure out other possibles and other humanities and other possible. So as a matter of fact, I'm currently working onto a movie which is called Red Moon, which is investigating some of these ideas, right? And the assumption is, so this movie, I'm working together with 3 families. So I have one family in France, one family in Armenia, and one family in Algeria. And we are all looking like each other. The baseline of the movie, it's a documentary. We are all looking at each other and it's working from the basis of, so this is one of my doppelganger, Lucia, who is based in Armenia, another one who is based in Algeria. And the idea there is to say, well, their family have experienced colonization and the family of Lucia has experienced the Armenian genocide. So has experienced, the worst of, humanity in a way. And my family is coming as a migration of these two in a way. And the assumption, the hypothesis there, if we were to be taking a kind of a scientific mindset, is that these families, when they think about the future on the moon, are going to come up with moon utopia that are going to be different from the current Elon Musk or the current Tesla, Blue Origin, Amazon kind of like vision as to how the future should look like. And so, of course, it's a film that is currently being developed at the moment, and I will hope to share some of these different visions in the upcoming future. And while I've got you on the line as well, and I'm going to stop here because I'm obviously like it's 10 minutes, so it's quite short, and I'm only here to really kind of crack some conversation here, and we can go in more detail about what the International Space Orchestra is about anyway in a later time, but we've been going on for 10 years. But while I've got you all here, I would like to share with you a bit of a top secret. I'm doing a bit of an exclusive here for Chloe McClellan, who is an incredible human that has blessed her with a presence today. But I'm going to share with you something that I will hope you're not going to share on social media because it's completely top secret until the 21st of October. But we won a bid, which is a nationwide bid here in the UK. That makes us basically one of the team that are going to deliver a nationwide festival, the Festival of Britain, effectively in 2022. And I want to share with you that this entire festival is going to be about the moon. And it's going to be about radical imagination. And it's going to be about also redistributing wealth. So that grant that we won, we're going to redistribute towards bursaries for 18 to 25. So if I have 80 to 25 year youths on the line, take part in Tour de Moon. I'm cracking up a lot of secret here. We will have open call available on our website, tourdemoon.com on the 21st of October, which is when this project is going live to members of the public. I'm not going to go in the great detail because it's completely secret until the 21st of October. But if you would like to take part in this festival that is going to take place all over the UK in 2022, and that you have project that you will want to get commissioned, because that's what it's about bursaries to commission new piece of work, and it's about new vision for the future and new vision about what we should do and collaborate on with the moon, not on the moon, then please take part. And also, if you are running an agency, if you have and I know some of you have also Arduino Sat or any other industries, we are also interested to collaborate with you. And it's a global festival. It's not just in the UK. There is multiple international partners. So I'm going to stop here, and please don't share this because it's secret until the 21st of October. But just be aware that on the 21st, there is an opportunity for you to get some project commission, especially if you have some vision for the future that are a bit different than what we have currently in place.
Nelly, that was so incredible to hear. Totally blown away by the fact that the project is also about the moon. It's amazing. Very surprising as well. That was top secret even to me. So yeah, thank you so much. So everybody, I'm sure you've all got hundreds of questions. Please put them in the Q&A box. I'm going to start. We're going to speak to the whole panel. Just because we've just spoken to you, Nelly, we can ask one question to you and then we'll kind of move around. I guess we've got a question that's come in about how we can avoid colonization on the moon when there are so many nations and nation states involved in developing the programs. Can you speak? You're on mute, I think.
Sorry, is this for me?
That's for you, Nelly. You go, because we just had you. Let's go.
So how, how can we avoid colonization of the moon, you mean? I mean, for me, it's coming down to I guess in a nutshell, this presentation that I've just given is, for me, there is a clear need to actually start to commission and support new visions that are not just ingrained into nation states. So obviously, there is a reality that is, of course, that budget, to put anything into outer space costs a fortune. And really, when it comes to it, yes, there is privatization of outer space. Yes, there is companies, but the reality is they cannot do anything without actually having the backing of the US government, for example, which is why NASA has got public-private collaboration, because you're going to need to have the anchor of a government in order to send anything in outer space. So it is, at the end of the day, very much a replication of what we have currently on planet Earth. And that, to me, is the core issue of the problem. So we need to start going straight into, the United Nations, having this conversation. There is actually a committee which is called the Peaceful Use of Outer Space Committee, which is based in the United Nations, where some of these questions are being discussed. But for me, it's where it's going to take place is we need to start having a global decision that is being taken, that perhaps space cannot be dealt with the same way that we are dealing on things on Earth currently, because I don't think that the model of just replicating what we have here above makes any sense. And that rational, just someone will have to explain to me, why is this rational making more sense than another that might be a bit more about cooperative or democratic or federalism or other form of politics that are available to us at this point in time, or other political philosophies, basically.
Thank you so much for that, Nelly. Do any of the other speakers have any ideas on that or any thoughts? You can shake or nod your head. Yeah, go on, Rod. Fire away.
Yeah, I'd like to add some notes, some ideas. Right now, the US is the leading country, and they are the one who make the policy. The main reason is that they just can. Right now, unfortunately, only the US had enough technologies, enough economic power to explore the moon. So one of the questions would be to, but it's really question related not to one nation, but to the whole nation. But in general, humanity has to build several ways to reach the moon. Unfortunately, there are no other companies who are reaching the moon outside the US in the next 2 years, except Japan. So the first thing is that humanity has to build a lot of different ways to deliver something to the moon. And the second comment is that in general, again, it's a global question, but from my perspective, we need a way to balance the way how proprietary companies get benefit from exploring the moon, or in general resources outside the Earth. I believe that there should be some kind of a tax, but a global tax for this company, and this tax, money from this tax should go to maybe UN or something like that, and this money should be used to make the life on Earth sustainable. Yeah. So that's what I want to add.
Yeah, that was fab, and I love the idea that both you and Nelly, looking at it from totally different perspectives, are still talking about this idea of cooperative, which is really exciting. I mean, I don't know, James and Mariana, if you've got anything you wanted to add, but don't worry if not, because there's plenty of questions. So
Well, I'm nothing particularly stunning to add, but I would just say, you know, it strikes me, you know, as an academic, just my world is the science, but at the same time, you know, we look at the space industry and we look at space exploration, and it strikes me that it's still very competitive. And I don't really understand why it has to be so competitive. You know, China at the moment has a very successful lunar exploration program, but it's still seen as kind of anti to the US-led and ESA to some extent, the European-led programs. And I think, you know, that we need to kind of get over that. How we do that, I have no idea. But, you know, Nelly mentioned, you know, it's got to come from the UN level. And, you know, everyone in the science and exploration of space has to kind of acknowledge all the opportunity and excitement that comes from a diverse range of countries and people getting involved in space exploration.
Thank you so much, James. That's great. Mariana, did you have anything to add? Don't worry if not.
I think this is a political discussion, I guess, where I can't really comment, but in either way, if you're private or country specific, I think you shouldn't forget the citizen to get them on board, because otherwise you don't have the ground to make a good argument to go in space. So I think we should always also think of the individuals as well.
Yeah, I totally agree with you. And now we'll jump onto a kind of totally different topic. We might be jumping all over the place, but these are some of the questions that have come from people in your audience. So one is for you, James, actually. You showed some small lunar samples. So if mining on the moon becomes a reality, how easy will it be to bring back those big samples?
Well, Apollo did it really well. You know, Apollo brought back hundreds of kilograms of rock. So, you know, with enough budget and with enough energy, you can get, you know, reasonable amounts of material off the lunar surface. But I think the key thing for lunar resources is using them to then drive further exploration. So we're not really going to be bringing back large amounts of material from the moon to the Earth because of value. We'll bring it back because of scientific value, but not financial, because there are very few rocks on the moon that are worth a lot of money, to be honest, apart from the fact they're moon rocks. But the resources within them, like water, which can help, you know, ongoing exploration of the lunar surface, like things that can be used for fuel that can then drive further exploration into space. You know, launching from the moon is much easier because of its smaller gravitational field. And if you've got resources you can use to help ongoing exploration from the moon surface, that's very valuable.
Well, thank you, James. That was wonderful. I don't know if anyone's got anything to add for that one. Otherwise, I will jump on. Yeah. Okay, I'm moving on. So something for you that's come in, Mariana, and I think you kind of touched on it a little bit in your presentation. It looks kind of, in the images you showed of everyone kind of on the ISS, it looks really small, looks really cramped. How realistic do you think it is to kind of alter and change these type of environments?
That's a really, really good question. And I guess I should stress these are conceptual designs. And I would love to discuss the reality and realism of those with people who are actually in the design of those spacecraft. I mean, we have the Center for Space Health, Space Medicine at UCL, and I started a discussion, and there are more and more kind of like papers out there as well, which say, well, you wouldn't easily change those because I think, as Nelly also mentioned before, there's a lot of money involved. So it's like, what can you realistically do? But I think if we don't start thinking about those opportunities now, how we design for it, we are not going to be ready in 20, 50 years. And I think there is now a momentum where so many private and government space agencies really pushing to go back to moon and to go to Mars and do those kind of explorations as humanity has always done. Then I think it's right now the perfect moment to think about those things which are really human-centered, because otherwise it's too late. And I don't, maybe not everything will be implemented, but even if it's just minor things which make a little tweak and will have an impact on the experience we will have there in space, then I think that is already a big achievement.
Yes, and anyone else got any thoughts on that? About changing environments in space? No? Okay, don't worry. So Rod, I think this is a question that's come in a little bit for you. I think using the kind of tools that you have available to you, how long do you think it's going to take to map the surface of the moon using your robots? And they're 10 meters.
It's quite a complicated question.
Yeah.
Right now, I do not remember all of the values out of my head. In general, our robot is able to, his maximum speed is around 1 meter per second. So you can do the math by your own, but basically each second it can map 1 meter. It's not the most correct assumption, I have to say, but it's really rough. And we are planning to send in one mission later, not during the first mission, but later we are planning to send 4 robots. It means that we'll be able to map the lunar surface 4 times faster than with one robot. So in general, it's quite safe to assume that we can map 1 meter per second during one lunar day.
And I guess the next question coming on from that is, what will you do with that data? What's it going to? What do you hope to find, and what's it going to tell us? And what do you think we'll be able to do with it?
Well, first of all, our main focus would be on the robot itself. So the most important for us is to get information about robot performance in real conditions. Later, we hope that we will be able to sell all the information that we received, both technical and scientific, to entities which are interested in it. And after a while, we would open all the data to wide public. In terms of what we want to find, after all, we want to find a place for a sustainable human base. So that's the ultimate goal, and all the information that will be collected during this period would be used for commercial and scientific purposes.
I see. I didn't actually realize you're looking for a base for human beings on the moon, or is it more you're thinking about deep space in the future?
We have a lot of things in mind. Of course, we'll be interested in deep space, but right now we are focused on the lunar surface.
Well, thank you so much.
Even on lunar surface, there are, I'd say, thousands of different things that must happen before it will be possible to have a really sustainable base and a possibility for maybe not an average, but let's say almost ordinary person to go to the moon. It'll be possible maybe in several decades, and we believe that it will be possible, and we are working on it.
Well, it's very exciting, so thank you for that. I think we've probably got time for just one more question per person, so I'll race through to the next one. This one is, I was going to read, Nelly, are you still there? Because if not, yes, sorry, just one that's come in for you is all about, I think, your earlier projects and how important it is for kind of those people on Earth to feel similar experiences to those people in space.
I mean, I think this is, to the point of Mariana. I mean, this is the big issue with space, isn't it? It's the fact that only a few of us will ever become astronauts, or will ever kind of like have that experience of seeing the Earth from space, right? So I guess the premises for me is to actually look at ways and means by which you can experience some of that that reach or some of that new scale or understanding that new scale, because I think at the end of the day, this is about scale, right? It's about understanding that we as humanity are only one tiny part of a gigantic universe, and that perhaps that, I mean, very likely there is other civilization that have been taking place, which is the baseline of what we do at the SETI Institute, right? The Search for Extraterrestrial Intelligence Institute is to just take, start from there when you look at the scale of the universe. So I guess for me, it's not so much about, like actually really going there. It's more about actually getting the leap of the mind to understand that we're just a tiny element there, and perhaps influence the way that we act here now on Earth, and actually use this as a means to, perhaps engage member of the public with real issues that are happening on planet Earth. I think once you understand that what we have here is actually what we have to deal with, which is planet Earth. And yes, you do discovery. Yes, you do exploration. Yes, we have that curiosity, and we are a species that is to be granted for wanting to always go out there and look for the rest. But at the same time, we also need to take care of what we have. And actually, I think space is a very good, landscape or action or mode of action in a way, or, like once you understand that all you have is this planet in a way, and that we're not going to be going anywhere soon. We're not going to be moving the entire planet into the moon, or Mars. Then perhaps, I think we get a certain leap there.
Thank you so much for that, Nelly. I don't know, Mariana, maybe you have something else to add to that. I'm not sure. No, don't worry. I'm picking on people.
I think Nelly said it so well. I mean, I agree. There is like only a few of us going there, but that doesn't necessarily mean we don't need to care about how to design their space trip. I mean, if 100 years ago someone would have planned what we now plan, maybe we would be able to go and we would be grateful. But I think it's all about like using our imagination and using our passion for it to hopefully make it better for the future. The same as we do on Earth. Hopefully we can make a difference for future generations if it's not good for us or happening for us.
Amazing. Well, thank you so much. And to kind of jump, it's a totally kind of different topic almost, or very much more specific topic, and it's one for you, James. It's just asking about if you use any data sets from other missions, such as Lunar Prospector or Smart 1. Don't know.
Yes, definitely. So, yeah, I mean, there's a whole range of instrumentation, lots of missions. I didn't mention them in the talk, but we collaborate with loads of people. And I think that's something really exciting about modern science is you cannot do it in isolation. You need to collaborate with lots of people, different institutions, different countries, in industry and in academia. And so we collaborate with people that study data from different spacecraft, particularly Lunar Prospector was really useful, as well as the Kaguya, the Japanese sort of follow-up mission, which gave us mineralogy of the surface. So it used spectroscopy, to study the mineralogical makeup of the lunar surface. So more than just looking at images of features, we could actually start to look at what things were made of and use that information to help us to refine hypotheses and answer questions more carefully. So yes, lots of different mission data. That's not my area of expertise, but I work with other people that do that kind of work.
Fabulous. Thank you so much, James. I mean, I saw a question came in a little bit about you're really enjoying this talk, which is great. Thank you. And how to, how you can also study these theories. Well, James teaches at the University of Portsmouth, Mariana at UCL, and Nelly also runs her own university, the University of the Underground. All of which we'll share, the information is kind of on our website, but we'll also share it with you in an email at the end. So just so you know, you can study all of this in a variety of different places. And I think there's just one more question, which is just one for you, Rod, before I think we dash off, because we've only got a couple of moments left. It's just all about testing, how exactly you've been testing those robots on Earth. How do you replicate the moon?
Two things. First of all, we have to replicate mass, and it's quite easy. We just attach it to straps, and we reduce mass by any amount by, I think, factor of 6. So it's not so hard to replicate math. It's much harder to replicate lunar dust, and it's right now you can buy lunar imitation of a lunar regolith, but unfortunately it behaves differently from the one on the moon, because lunar regolith on Earth contains some moisture, and because of that, it acts really different from the one on the moon. So basically, to deal with mass, we just attached some straps or helium balloons, and to imitate regoliths, we had to use really huge vacuum chambers, and that's it. In general, we just make tests step by step. So we create some subsystem and make some tests. When we understand that in general a subsystem works as expected, we integrate it, then we conduct more tests, and so on. So it's like a test cycle.
You said it was quite easy. Doesn't sound it to me, but I'm excited to hear it's happening. And to be honest, we're at 28 minutes past, so we've only got 2 minutes left. So I'm going to start to round up. I want to say a huge thank you to our speakers. Space Week is a really busy week, and we're really grateful you've been taking the time to speak with us and kind of share all your knowledge and expertise. And it's a great range of, academic, what's happening in the research and what's actually happening in the commercial side of things as well. So thank you so much. We're really, really grateful. I want to say to everybody that's joined us today, we are going to be doing more of these inspirational talks. So please do sign up to our newsletter, where we'll be sharing a bit more information. And you can also follow us on Twitter and on LinkedIn too. And if I'm sure we'll be sharing a little bit more information about our speakers and things via email afterwards. And I want to let you know, I'll share all the details. So if you've got questions, burning things that you want to ask our speakers and follow up with, then you can also go ahead and do that with them directly. But yeah, that's it from me. Fabulous. Thank you so much for taking the time, and I'll see you again.
Thank you, Chloe. Well done. Thank you all. Thank you for inviting
Thank
us.
you.
Bravo, bravo.
It's been so fun to see you.
Have a fantastic Tuesday.
Thank you. Bye all.
Bye.
Bye.